In September 2008, after decades of anticipation, the world's most advanced high-energy particle collider, the Large Hadron Collider, LHC, became operational. Built by the European Organization for Nuclear Research, its construction was painstaking. Over the years, the LHC has significantly enhanced our understanding of the universe. However, a recent development has truly baffled physicists. Upon amplifying the LHC to its maximum beam of energy, certain scientists detected an unexpected and anomalous result. Since then, the scientific community has been buzzing with theories attempting to explain this anomaly. What happened that was so catastrophic, and what are its implications for us in the present and the future of the scientific enterprise? Stay tuned as we discover all this and more secrets ever imagined. Imagine a massive machine so vast it spans across 2 countries and dives deep beneath the Earth. Welcome to the world of the Large Hadron Collider, LHC, a masterpiece of human achievement built by CERN. This isn't just any machine, it's the world's largest and most powerful particle collider, and its story is as compelling as its purpose. CERN, the European Organization for Nuclear Research, is a beacon of international collaboration and scientific curiosity. Its origins trace back to the post-World War II era when Europe was recovering from the devastating conflict. There was a growing consensus among scientists and policymakers that collaboration was the key to rebuilding the continent's scientific prowess. In 1950, the renowned physicist Louis de Broglie proposed the creation of a shared European laboratory to rekindle scientific innovation and strengthen peaceful cooperation. Soon after, in 1952, 11 countries came together to sign the CERN Convention, establishing the organization. By 1957, CERN was officially up and running on the border between Switzerland and France. The primary objective of CERN was to research atomic nuclei and their constituents. To achieve this, particle accelerators were required. These immense machines propel particles to near light speed, smashing them together to reveal insights into the universe's basic building blocks. Fast forward to the 1980s, and the idea of the Large Hadron Collider, LHC, began taking shape. As the ambition of scientists grew, so did the need for a more powerful machine to probe deeper into matter's mysteries. The LHC was conceived as the world's largest and most powerful particle accelerator, boasting a 27 kilometers range of superconducting magnets and detectors. Construction of the LHC began in 1998 and was an engineering marvel in its own right. Situated 100 meters underground, this giant loop required collaboration from thousands of scientists and engineers from all over the world. It took a decade to complete, and in 2008, the LHC was ready to start its particle-smashing journey. But why so deep? Well, apart from shielding the collider from the world above, the depth cleverly avoids the challenging terrain of the Jura Mountains. By doing this, there was no need to dig a massive vertical axis, saving a significant chunk of change. After all, who'd want to buy expensive land on the surface when there's ample space below? But what exactly does this massive underground ring do? In 2010, it achieved its first ever particle collision at a mind-blowing energy level of 3.5 teraelectronvolts per beam. To put that in perspective, it was almost 4 times the previous world record, and that was just the beginning. After some upgrades, it now boasts an even more impressive 6.5 teraelectronvolts. Imagine 2 beams of particles racing at near light speed and then colliding. That's the LHC for you. It has 4 specific points where these high-speed particles meet and collide. Around these points, 7 detectors eagerly wait, each designed to observe and unravel various phenomena resulting from these collisions. Most of the time, the LHC smashes together proton beams, but once a year, for an entire month, it turns its focus to heavy ions like lead. It's like the machine's special annual event. Now you might be thinking, Why go through all this trouble? The answer lies in our curiosity about the universe. Physicists are using the LHC to test some of the most mind-bending theories of particle physics. They're especially keen on studying the elusive Higgs boson and probing the existence of a vast family of particles from supersymmetric theories. Ever heard of hadrons? They're tiny subatomic particles made up of even tinier things called quarks. Picture them as the building blocks of protons and neutrons. The LHC is named after these because it collides them to produce byproducts. Many of these byproducts exist only for a fleeting moment and can't be studied any other way. So, every time there's a collision in this massive underground ring, it's like a mini Big Bang. Scientists then get a glimpse into the very essence of our universe, its building blocks, and the forces that stitch it all together. Constructed between 1983 and 1988, this underground tunnel is a massive 3.8 meters wide, safeguarded by concrete. Above the ground, there's a building filled with essential equipment. Imagine a room packed with complex control electronics, compressors, ventilation gear, and cooling systems. Now, here's where it gets mind-blowing. The LHC produces around 15 petabytes of data every year. That's a massive amount of information to handle. An international collaboration gave birth to a computing grid built especially for the LHC. This network is a tech marvel in itself. The LHC's main mission is to uncover the secrets of a mysterious particle called the Higgs boson. This particle was like a ghost. It was predicted by scientists but had never been seen. It was so elusive because of its high mass. The LHC, with its powerful capabilities, aimed to produce several of these Higgs bosons every minute. It's like setting a trap for a rare creature that many believed existed but had never been captured. And the LHC didn't stop at that. Besides hunting for the Higgs boson, it explored other uncharted territories of physics. It searched for supersymmetric particles and other unseen wonders of the universe. However, it wasn't all smooth sailing. Just after it started in 2008, the LHC faced a significant setback. A magnet malfunction damaged many parts of the collider, delaying its tests for over a year. But once it started its operations between 2009 and 2013, the LHC made some groundbreaking discoveries, including finally spotting the elusive Higgs boson. After its first successful run, the LHC went into hibernation for upgrades, reawakening in 2015 ready for more adventures. Its second run spanned from 2015 to 2018, followed by a pause until it rebooted in April 2022. Now, with a boosted beam energy of 6.8 TeV, this machine's third run is set to captivate us until 2026. But something extraordinary happened on July 7th during its third run. Imagine Earth's magnetic field as a protective bubble around our planet. On that day, a mysterious crack appeared in this bubble. This wasn't just a fleeting glitch. It stayed open for a whopping 14 hours. Think of a window suddenly left open on a stormy night, letting the chilly winds rush in. This crack allowed a flood of solar winds from the sun, leading to massive geomagnetic storms. The result? Dazzling displays of auroras in the sky. If you're a fan of Stranger Things, you might recall the monstrous villain Vecna. Some fans humorously wondered if Vecna had emerged through this very crack. While that remains a playful theory, the visual treat from the auroras was undeniable. But why did this crack form? The culprit is known as a co-rotating interaction region, CIR. From the sun, CIRs are vast plasma structures created when different speeds of solar winds interact. Imagine two rivers, one slow and one fast, merging into a tumultuous waterfall. These CIRs, along with other phenomena like coronal mass ejections, are thrown from the sun towards Earth. When they hit, we get a light show, the auroras. Such a CIR collision led to a lasting geomagnetic storm. The National Oceanic and Atmospheric Administration, NOAA, even noted that this storm was supercharged by a preceding coronal mass ejection. Should we be alarmed by these CERNs? Interestingly, experts give a reassuring no. Earth's magnetic field, our protective shield, regularly sees such cracks. These usually close up swiftly. However, recent events show they can linger for hours. Imagine living in a house during a storm with a window that occasionally gets stuck open. Though most of the storm is deflected, some water might ruin the couch. Similarly, while our magnetic shield deflects most space storms, some energy sneaks in. This can sometimes play havoc with our satellites, radios, and power systems. In 2003, Harold Fry likened our magnetic shield to a drafty house. Most storms are kept out, but occasionally some energy slips through the cracks, sometimes just enough to create a spectacle in the sky or to mess with our tech. Thankfully, there were no resulting radio blackouts or power outages. Instead, this cosmic event brought a stunning surprise for the residents of Canada and the U.S., awe-inspiring northern lights. But there's more. Scientists have let us in on a secret. The sun is becoming more lively. In fact, it's showing more activity than they anticipated for this time in its cycle. What does that mean for us? Simple. If you've ever wanted to see an aurora, your chances just got a lot better. Over the next 3 years, expect the skies to dance with colors even more frequently. And speaking of monumental scientific revelations, let's talk about the Large Hadron Collider, LHC. Think of the LHC as a massive microscope helping scientists observe the tiniest particles in our universe. Back in July 2017, it uncovered several incredible findings, like the properties of the Higgs boson. Fast forward to 202. 1, and the LHC had identified 59 new hadrons. And in July 2022, a new particle was observed called the pentaquark, made up of unique combinations of quarks.